Um, so I threw quite a lot at you on Thursday in terms of atmospheric stability. Something on the here's what I plan to do. Oh, first of all, I sent you an email. So I've updated the schedule. And I think it's probably merciful to not have exam on the Tuesday that you get back from spring break. But key. So things still line up pretty well. So we will do. I'll tell you a little bit about how I'm going to structure this morning. Thursday, we will get to the thermodiagram, which is the take-home exercise. Following week will be probably a bit more on the take-home exercise. And then thunderstorms. And then we'll do spring break. And we'll come back and we'll have a week, which will be a lecture and a review session. And then we'll do exam number 2 on the 1st of April. And that one's very important. Okay. So that's the first little bit of housekeeping. Second one is, what I want to do this morning is look at some output and some surface analysis for obvious reasons. We had something come through at 4:35 a.m., which was pretty cool. And even though we're not there yet, we haven't done severe weather, and we haven't talked about linking surface with upper levels and vorticity and things like that. There's still quite a lot to come. I thought it might be quite useful to just show you the types of things that we've been talking about as it pertains to this morning and what happened. Okay, because it's probably not going to come as a surprise, and it'll be no secret that when it comes to the final exam, and I give you that integrative assessment, you're probably not going to get a bunch of maps where there's nothing happening. And chances are you're probably going to get a bunch of maps where there's some cool stuff happening, like severe outbreaks and tornadoes and thunderstorms and stuff like that. So I want to get you used to, if nothing else, the terminology that we're going to be using, so that when we do get to severe weather and numerical weather forecasting, that that will hopefully bring it out. So let's look at a few things first in terms of what's happened in the last couple of hours. Then what I want to do is I want to go back and do a very quick review of what we covered on Thursday. I know I went live to the sounding on Thursday, and maybe that confused you more than it should have. So I'm going to go to the lecture material and use the sounding on the lecture material just to review some stuff on that. Then we'll talk a little bit about how you change stability, and then we're going to get to look at precipitation processes and then cloud classification. So a mixed bag this morning. But let's spend a bit of time here first, I don't know, 10 minutes or so, just looking at some of the maps. Here's the surface analysis at midday, March the 4th, Greenwich Mean Time. So that's 6 a.m. Yeah, March the 4th. So this is 6 a.m. Texas time. So this is only a couple of hours off. Okay. So who wants to have a stab? What do you notice? Let me scroll down just a little bit and then just zoom in a little bit. Oh boy, that is absolutely darn classic. Okay. What do you notice?
We have a cold front.
Okay, so we've got a cold front. Yeah, so there's the cold front, right?
Which causes like thunderstorms and stuff.
Yep. Okay, so thunderstorms. Just looking at the station models, these are all thunderstorms, fog, rainfall, heavy rainfall. So there's the cold front. It's the low pressure. This is the warm front, right? The purple one here, we haven't talked much about. We're going to look at that in a fair amount of detail. That's the occluded front. So this whole system, okay, I should probably save some of these images just to come back to it when we actually get to the mid latitudes. This whole system here with the central low pressure, the cold front, the warm front, the occluded front, and what's going on in the upper levels is known as a mid latitude cyclone. Okay, this is the major storm system that we get in the mid latitudes. at least at large scales. Okay? And as we will talk about after exam number 2, what these systems are basically relay switches between the warm tropics and the colder poles, right? Allowing warm air to move northwards, like you can see here, okay, and cooler air to come back from the north. So you look at this sector here, right? This entire region ahead of the cold front. This is all known as the warm sector. Okay, so you can look at temperatures and dew points 67, 66, 69, 68. 68 is pretty high dew point for this time of the year. Remember, what's a really high dew point? About 75, right? That's a really high dew point. But at this time of year, sort of very early spring, technically not even spring yet, those are pretty high dew points. You can see all of the air is out of the southeast, right? Pretty gentle. And then we have this cold front coming in. I'll show you the sounding in just a little bit from Fort Worth, so you can look at that. Look at the pressures here, 992 millibars. Okay, so that's pretty low there, not too bad. If we didn't have this cold front coming through, okay, we wouldn't have had, well, we certainly wouldn't have had any kind of thunderstorms, because the atmosphere, the lower atmosphere right now is pretty stable. It may seem odd. We have this dramatic line of thunderstorms coming through, and that's being driven solely by the cold front. Remember, and I hope I made this clear on Thursday, but I'm going to reiterate it again this morning. Okay? Stability of the atmosphere just tells you the potential. What is the potential for air to go up or down? That's it. Okay? Doesn't say it's actually going to happen unless you have some kind of trigger, right? And the trigger that came through at 5 a.m. was the cold front, right, into this fairly warm, moist air. And that warm, moist air had nowhere to go but vertically upwards as that front raced on through. Does that sort of make sense? Okay, anything else on the surface map that you want to ask about before we go and look at some other stuff? Okay, so that's the surface map. Let's look at the sounding here for a second. So this is the sounding, this is a little old, so they only do the soundings every 12 hours. So this is, they haven't done the one this morning. So this is midnight last night, Greenwich Mean Time. So this is 6 p.m. last night. So we're 12 hours behind schedule here. But when you look at the sounding last night, okay, I'm just going to draw it in red here. So remember, on the sounding, we've got 2 lines, right? We've got the actual temperature, which starts here and does that, does that, and does that. Then you've got a little inversion there. So on the right is the temperature, on the left is the dew point, right? That just shows you what the vertical temperature and the moisture content is as you go up with elevation. Remember, the dew point is the actual amount of moisture in the atmosphere, right? And if the temperature and the dew point diverge, that means you've got much drier air there at that particular level, right? So when you look here, so this is last night, right? The temperature's there and the dew point's there, okay? And then we go up, we only go up about 500 to 600 meters, and the dew point and the temperature are very close to one another, okay? Which means it was fairly moist as you went up with altitude, okay? Dew points and temperatures pretty close, and then we get to about 2.5 kilometers, and we've got this divergence here. We've got this pool of warmer air. The point on this one, everybody, is you can actually ignore the dew point for the moment, right? Because when we talk about stability, what we really need is the temperature profile, okay? And then we're going to take our little theoretical parcel of air and see what our theoretical parcel of air would do, right? So we're at the surface here. So let's just say this is the surface temperature right there. Okay, so that's the surface temperature at 6 p.m. last night. And this black line is the temperature profile. Now I'm going to draw in red what this parcel would have done along the dry. I know you can't see this because it's a light gray here. That's the dry adiabatic black gray right there. Okay, and then this is the saturated adiabatic black right there, following the green curves. Kind of see that at the back there? Okay. So, what do you think? Just talking about the overall stability of the atmosphere. Temperatures here. Maybe I should draw the temperature profile in green. Now this is pretty big to see. But there's the lapse rates, and here's the temperature profile. Yeah, that's. That's the temperature. Who wants to have a stab at talking about the stability characteristics of the atmosphere here? The red line, remember again, is your hypothetical bubble of air. Hypothetical. What would that parcel of air do? What do you say here? The red line is the bubble of air. The red line is just to the left of the environmental lapse rate, right? The environmental lapse rate is the green temperature profile. What would this parcel of air do right here? It was to be, if it was to be lifted to this point. Right.
Go back down.
Why?
and close.
No, it would go back down
That's why
because
it's warmer than.
if it's warmer than the surrounding air, then it would be unstable and it would keep rising. Other way around. Okay, I know it's kind of hard to see it. You'll see it better in just a second. Okay. So again, remember the greenish line here, this one that I tried to color in, is the environmental lapse rate. They actually lie right on top of one another here. Okay, your bubble of air lies right on top of the environmental lapse rate. Those two are literally right on top of one another, which would technically be what? What kind of atmosphere? Oh, good, a neutral atmosphere. Because if you took your hands off the parcel, its temperature would be exactly the same as the surrounding air, right? And it would just sit there. But when you get to this level here, okay, and so this is the lifting condensation level, right? It gets to the dew point there. Right? Don't worry why that happens right there. You'll get more familiar with that when we look at the thermodynamic. But at this point here, the temperature in the parcel is cooler than the environment. Therefore, if you took your hands off it, it would sink back down, right? So it's stable. And it's stable, and then it lies right on top of it. Okay, and it goes, and then it hits this, and this is called what when temperature increases with height? That's the inversion, right? The inversion, the inverse of the norm. And you can see, I hope, why inversions are the most stable situation you can get. Because look, if, all hypothetical, right? If your parcel is still rising and it gets to this point over here, it stops right there. It can't go through the inversion, right? Because if it did, if it tried to get through the inversion here, it would immediately be much colder than the actual environment, and it would sink back down. So anytime you see an increase in temperature with height, that's the lid, that's the cap, the inversion. So there was a cap last night, and there was a cap this morning, right? And the only way you can get storms to develop, in other words, the only way you can have an atmosphere where the air is going to start shooting up is if you break through that cap. And there was only one thing that helped break through that cap, and that was the cold front. But the cold front came in and the atmosphere said, well, I give up. It doesn't matter how strong my inversion is, that air is going up whether you like it. Okay. Okay, so that's, I know that's 12 hours old, but it probably was quite similar this morning. We'll have to see if they update it a little later on. Then let me look at a couple of other things here. Okay. We'll go to the model analysis. This is 2 meters above ground level dew points. Ooh, yummy. When is this valid? This is valid for 12Z. So this is 6 a.m. this morning. Here's the dew points at 6 a.m. this morning. Right? So there's that big tongue of warm, moist air out ahead of the cold front. Okay, and look how dry the air is behind this cold front. So here are the dew points, 69, 65s, right? That's that thermal influx of warm, moist air ahead of the. So we've got plenty of moisture there available. Okay, everybody with me? So that ties in with the surface map. What else should we look at here? Here's the relative humidities. as a percentage. Yeah. Relative humidities. Turn the lights up one more so you can see this a little more better. There we go. So here we are, 90 to 100%. So the relative humidities in the blues here are all 100%. These are sort of 90%, right? We're right at the surface. The temperature this morning was whatever it was, 66, and the dew point was 64. So at the surface, we had 90+% relative humidity. You didn't have to go up very far, and your relative humidity to 100%, right? As you get to the lifting condensation. So that's quite cool. Let me look at a couple of other things here. So that's surface. Here's the upper air. Let's start. Okay, here we go. Okay. Here's the upper end. Here's the 500 millibar surface. How do you, well, I mean, it says 500 millibar surface, just look between. Look at the heights here, 5820, 5,800 meters, 5,007, 558. Okay. Someone talk to me about the 500 millibar surface. If I gave you this in exam right now and said, for 3 or 4 points. What's going on at the 500 millibar surface here? What do you notice? How would you describe the 500 millibar surface over the great state of Texas?
Increasing in height pretty rapidly as you go towards the northwest.
Which means what? Good, nice observation.
That there's a lot between.
Yeah, there's a steep pressure gradient, right? So if there's a steep pressure gradient, that means the wind's moving pretty quick, right? Remember, the tighter the isobars are getting packed. This is a steep pressure gradient. And the wind speeds here are 75 knots, that's 60 knots, that's 75 knots again, that's 60 knots here, okay? And the gentle pressure gradients here, 35, 30, 25, 30, the gradients spread apart, right? So that's a good observation. How else would you describe the upper levels here? Any ridge, any trough? Start trying to look for those immediately when you look at a map.
There's a trough.
Right, so deep trough here. And there's a ridge over there, right? Pretty darn classic. If I was to pull up, and I haven't looked at it yet, but let's look at the jet stream. Okay. So jet stream, we're going to go to 300 millibars. Oh, bazinga. Okay. So here's the jet stream at 300 millibars, right? 9,480 meters up. So here's the base of the trough here, right? Wind speeds here are 120, 155 knots. Here's the core here of the jet stream. Oh, okay. Oh no, that's 140. That's 155. That's the fastest I've seen. Yeah. 155 knots. So here's the trough, right? So the jet stream is meandering down, allowing for that cold air to drain south. Cool. Okay, I'm going to go to another one here. I'm going to go back to the 500 millibar. Where's this going to be? This is going to be upper air dynamics. Okay, I know we haven't done this yet. So this is the 500 millibar surface. And the color shading on this is what we call vorticity, that's spin. I know we haven't done that yet, so don't panic about that, right? It's the spin. And the quick analogy here is the ice skater. Right? So when an ice skater wants to increase her rate of spin, she does what? She pulls her hands inwards, okay? So increase your rate of spin as you converge your hands towards the center of your body. And you slow down, diverge away from the center of mass, okay? So the fastest spin is around the base of the trough. What do you notice about the lines over Texas? They are, here's 573. They what?
Probably 3 apart.
Uh-huh. As opposed to the lines doing this. Ring a bell? When we were looking at the dead street? What's happening on the western side of a trough in the upper levels, the areas? Exactly, it's converging, going from an 8 to a 4-lane highway, comes around the base of the trough and then it diverges. Right? So the divergence on the eastern side here ties in perfectly with what happened this morning. That totally controlled what happened this morning. The divergence on the eastern side said to the frontal boundary, we've got an unstable atmosphere. We've got the lift that you need, right? The upper level divergence allowed that surface convergence to then break through that. That inversion was there. I know we haven't done that in any detail yet, but I just want to throw it out there to get the visuals going. Yeah.
What do you mean upper level divergence? Like, how is it diverging if they're all close together?
Okay, so what I mean by upper level divergence is think of it in this terms. If you are sitting right here at the base of the trough, okay, what the air is doing here is it's converging. Okay, it's literally coming together like that, coming around the base of the trough, and then it's diverging here. And if it's diverging here, it's allowing it to come up from below. Okay. Now, no, we've only just started to make that link between the surface and the upper levels. We'll be much more explicit when we get to the mid-latitude. So the bottom line this morning is we had all of the moisture conditions, right? We had all of this warm, moist air, high dew points coming in from the Gulf. Perfect. Okay. The air was potentially unstable, but we would never have had any of this line of thunderstorms unless we had a cold front coming through. The cold front was being driven by the upper levels, diverging from the eastern connected with the upper levels. Okay, 25 minutes. That was longer than I wanted, but I just wanted to. It seemed like it would be a miss if we were talking about instability and we didn't actually pull that up. Okay. All right. So let's go back to stability versus instability. Okay. So this was the sounding that was on the PDF. So I'm going to come back and just annotate this a little bit, and then we'll talk about how do you change stability. So just as a reminder, we've got pressure here, horizontal blue lines, the elevation, the altitude at which a pressure surface occurs. So 500 millibars is occurring at 5,810 meters. There's the wind on the right. The green lines are, can you remember? The dry adiabatic lapse rates. The blue dashed lines are the saturated adiabatic lapse rates, and the brown lines are the specific humidity or the mixing ratio, the brown at the bottom, right? So down here, we've got 30 grams per kilogram. So let me point out one thing, and then I'll talk a bit more about the dew point and the temperature. Notice down here, where the air is very cold, the dry adiabatic lapse rate and the saturated adiabatic lapse rate are what? They're pretty much parallel. Okay, meaning in very cold air, well, this would make a nice exam question. In very cold air, minus 50 degrees, minus 60 degrees, the dry adiabatic lapse rate and the saturated adiabatic lapse rate are very close to one and the same. What's the dry rate? By definition, 1 degree per 100 meters, right? The saturation rate is variable. But what I'm saying here is down here where the air is super cold, the two rates mimic each other. But when the air is very moist, here's the dry rate, it's at 1 degree, and here's the saturated rate. Changes much more quickly, right? It's this big loopy curve. Why? Why is it so different in the warm air versus the cold air? I've asked a question like that on exam number 1. Why is it different, right?
Honestly, in moist air, and it's easier to release maybe
Bingo, right? In the warmer air, nice. The warmer the air, the more moisture it, quote, can hold, right? So in very warm air, you've got much more moisture. Just remember your saturation vapor pressure. So the warmer the air, the more moisture. And so you release much more latent heat in that warm, moist air, right? Which changes the rate dramatically. Not from 1 degree Celsius per 100 meters, but something like 0.6 degrees Celsius per 100. But when you get into the very, very cold air, it doesn't matter. There's so little latent heat being released. There's so little moisture being held in that cold air that the two rates get very close to one another. Okay, so that's why the blue lines and the green lines
So it's
change
the-
like that. Nick?
So it's the saturated adiabatic blast rate that gets changed.
Yes, dramatically as you start getting more and more moisture into the air. Why? Because of our old friend, the saturation vapor pressure curve. So down here, not much change. Up here, dramatic change. Okay, cool. Okay, so what we're looking at here is the temperature plot. So the black line is the environmental lapse rate. Okay, and the second line to the left is the dew point. Now, on most of these diagrams, they'll plot the temperature in red and the dew point in blue, or they'll highlight the two. And so here they've just got them as two black lines. So this is the temperature, this is the environmental lapse rate, right? So there's your inversion. And then your dew point touches here, which means your relative humidity is by definition what right here? Got to be 100% if the dew point's touching the environmental lapse rate. And then it falls over to the left, meaning it's much drier air coming in. Okay, does that make sense to everybody? So then let me really emphasize this point and make sure you're all super happy with it. Okay? What you're looking at here is just the environmental lapse rate and the dew point. And that gives you a snapshot of the vertical structure of the atmosphere. What is the actual temperature and the dew point as you look at that atmosphere, right? So that is looking at the layers as you go up vertically. Okay. When determining stability, you have to come back to your hypothetical little parcel, right? If you're determining stability. So let's say we want to try and determine the stability, and we're starting at the surface. Okay. That makes sense? We're going to start at the surface here. Can I do this? Yeah, I should do this. Okay. This is really important. So I'm going to make up a couple of numbers here. I'm just going to extend that down right to the surface. So let's keep it simple. Let's say the temperature here is, well, let's say it's 28 degrees Celsius. Okay. And the dew point here is, let's say it's 18 degrees Celsius. At the surface, or where those two curves start. Temperature is 28 degrees Celsius, the dew point is 18 degrees Celsius. Right? Relative humidity is going to be what? 50%, 60%, something like that. Right? Because the dew point and the temperature are far away. Does that make sense? Okay. All right, cool. This brown line, that one right there. What is the brown line again? That's the specific humidity, right? That is the actual amount of moisture in the air in terms of grams per kilogram, right? Grams per kilogram, that brown line right there. Okay. And let's just keep it simple. Let's say it's going right through that 30 grams per kilogram of air. So at the surface here, we've got a temperature of 28 degrees Celsius, a dew point of 18 degrees Celsius, okay? And the mixing ratio, how many grams per kilogram of 30 grams per kilogram of actual moisture in the parcel atmosphere. Everybody good? All good. So that's your parcel. So as we go through this, and as we get in, especially when we get to Thursday in the thermodiagram, okay, please remember we're dealing with two things. We're dealing with a parcel and what happens to the parcel, and we're dealing with the ambient air around that parcel. You have to start thinking in those terms, okay, to determine stability, whether your parcel will go up or down, and what that really means. Okay, so your parcel here is at 28 degrees Celsius. It's got a dew point of 18 degrees Celsius, and that's about 30 grams per kilogram of moisture in it. Right? And now what happens if you start lifting that parcel? Okay. Here's a really tricky statement, but I hope this really sinks in. Okay. As you start lifting this hypothetical parcel from the surface, right, that's got those moisture and temperature characteristics, we're going to assume that it keeps the same amount of moisture in it. So here's your bubble of air, and it's got 30 grams of moisture in it. Okay? Everybody with me? As you lift that parcel, it's going to continue to hold its 30 grams of moisture. Which will make sense when we start talking about precipitation, because you'll see just how tiny cloud droplets are. Okay, they're tiny, tiny, tiny. And so in a bubble of air, as air rises, it takes almost all of the moisture with it. We're just going to assume it's 30 grams per kilogram. Everybody with me? Okay, cool. So here's your parcel, and I'm going to say we're going to lift that parcel. It is saturated or unsaturated? It's unsaturated. Okay, so as I lift this parcel, what rate am I going to use? I'm going to cool this parcel at what rate? The dry adiabatic lateral rate. Okay, the DALR, 1 degree Celsius per 100 meters, right? 1 degree Celsius per 100 meters. So I'm going to cool this parcel at 1 degree Celsius per 100 meters. We know that its dew point, the dew point in that parcel is 18, right? The dew point is 18. That's the temperature to which you need to cool that parcel for what to occur? Saturation. Yeah, right? So it's going to follow this, it's just going to follow the slope of this green line. Your parcel is going to do this, and it's going to cool, and it's going to cool until it reaches the dew point of 18 degrees Celsius, right? Wherever that is, 10, 15, 16, 17, 18, probably somewhere there. Yep. At which point it becomes, and then it starts cooling at the saturated rate, and it will follow that line there. Okay. Does the air parcel actually do that? Why not? Because why?
I was just gonna say, because the black line that is on the thing, didn't do it, but.
What's the temperature of your parcel here? Warmer or colder than the environment? Colder, colder. Here it reaches it. So this layer is by definition unstable because the temperature in your parcel is always colder. The environmental lateral always lies to the right of it. Okay, and then it stops rising here because it reaches, even though it wants to start rising at the saturated rate, it stops there because it joins the environmental lateral. There's your inversion, and it doesn't. Okay, so even though you've got you've got the potential for uplift, it's not going to happen because you've got the inversion there. Okay, so I'm going to just stop there and make sure everybody's happy with that. Again, you take a step back and you look at the overall environmental lateral rate, and then you can start with your little parcel of air. Okay, and lift that parcel of air along the dry rate until it reaches its dew point. In the thermodiagram, you're going to take it one step further, and you'll see exactly how that happens. Questions? So if we didn't have any trigger mechanism and you were making a forecast here, what would you say? Hopeless, right? Okay, this is the environmental lateral. Let's lift it, take our hands off it. It's colder than the environment, it will sink back down. It's colder than the environment, it will sink back down. Here it joins up the environmental lateral, and that's exactly where it's going to stop. All good.
So you said it's unstable, the environment or like the actual temperature is unstable, but it's crazy.
No, the parcel
The parcel that like me,
that you're lifting, right? Yeah, you'll see when we get to the thermodiagram, we talk about two different types of stability. One is the layer stability. So how do we look at an atmosphere and say which layers are stable or unstable? Just based on that. And then we look at your parcel stability. In other words, if you had a parcel here, would it go up or down? If you had a parcel here, would it go up or down? But that will become really clear when we do the thermodiagram. Okay, all right. So let's go on to how do we change stability? How does stability change? Because it changes all the time, right? Here's one way to change stability. Is to have radiational cooling at night. All right, so the sun goes down, especially on a clear night, and especially in winter, the ground gets cold and it cools that air in contact with the ground, right? And so when you get a pool of cold air at the ground and you have relatively warm air above, okay, that produces an inversion, right? So here's a parcel of air, and this is what your environmental lapse rate looks like in this example. So you've got an inversion right at the ground, right? You've got a pool of cool air and then warmer air above, and then it starts cooling as you get above that. So radiational cooling, rapid cooling at night, very frequently causes these low-level inversions, cools cold air with relatively warmer air above, and that stabilizes the atmosphere, right? Because if you were to lift your parcel of air from here to there, it'll sink straight back down, because it's much colder than the surrounding air. Radiational cooling is one way to change stability, okay? Here's another way. And this is very often what happens on summer afternoons, and that is if you heat the ground, right, you will change the stability. So here's a wacky little diagram that I've drawn in here. We'll keep numbers off here. Here's height and here's temperature along the bottom, right? Temperature and height along the bottom. And let's say we'll keep it super simple. Let's say the green line here is your environmental lapse rate. That's the temperature change with height. You send up your weather balloon and it sends back your green dot. Okay? Are you with me? So if that's your environmental lapse rate and you lift your parcel here along the dry rate, okay, and you get to this height, what would happen to the air parcel? Well, the temperature in your air parcel is much lower than the temperature of the environment. It's cooler and therefore it would sink back down. And even if it was saturated, I haven't drawn the saturated rate here, but if it was saturated, it would still be stable because your environmental lapse rate is not changing very much. Okay, but that's a stable environment. But if you want to destabilize that atmosphere, do this. Heat the ground, increase the ground temperature. Sun comes up, and if you've got rapid heating to this, okay, then look what happens. It decides it's going to actually behave. Well, so if you heat the ground to here, now your air temperature, the parcel of your the temperature of your parcel is here. It starts rising at the dry adiabatic lapse rate, and it'll keep rising until it gets to that position. If it doesn't reach its dew point, right? But if it reaches its dew point somewhere along that ascent to that point, and it reaches its dew point, then it'll cool at the moist adiabatic lapse rate. By heating the ground, you've shifted everything away from the environment and you've destabilized the atmosphere, because now this whole atmosphere is unstable because the temperature in your parcel, whether it's dry or saturated, is warmer than the environment. So that's exactly what happens on summer afternoons. Okay. Especially if you've got a lid, and we'll talk about that when we get to severe weather. If you can start heating the atmosphere, creating that kind of boiling pot in the lower atmosphere, that destabilizes the atmosphere because it shifts everything to the right. So that's another way to change stability. Here's another way. Cool the upper atmosphere. If you can have an infusion of cool air into the upper atmosphere, that destabilizes it quickly. Let's say your parcel's over here, so parcel initial level, right? And let's say that's your initial vertical sounding, right? So that's your initial environmental lapse rate. So this is 3 kilometers, and your weather balloon says your environmental lapse rate's doing that. And if your air parcel is saturated, which probably will be at 3 kilometers up in the atmosphere, it will cool at the saturated rate. It's always going to be stable because here the temperature is cooler than the environment. But if you cool that other upper atmosphere, then this becomes the sounding after the cooling, then that shifts your entire system so that your air parcel here along the moist rate is always warmer than the environment, right? So all you're doing here is you're looking at the interplay between your parcel and the environmental lapse rate. That's all it is. So how do you change stability? Cool it at the surface, cool it in the upper levels, or keep that surface in the summer afternoon. That will change the stability of the atmosphere. Right.
So if you cool the upper atmosphere, it's gonna shift toward the moist.
So, yeah, so in this,
That's the situation. Where the right line, I'm sorry, yeah, red line is over there.
this one here.
Yeah.
So this is, so what we're doing is we're saying, we're at 3 kilometers, right? So we're at this parcel level. And we're pretty safe to say that the atmosphere, that the air parcel is gonna cool at the saturated rate there, because you more than likely are in a very high level of humidity or pressure. So we're just dealing with the saturated rate.
Okay, so then when you cool it, it would go to the left.
Yeah, when you cool it, so this, say this is
So right down that way.
whatever, say this is midday and then it's 4 in the afternoon and you've got an infusion of cold air coming in, then your environmental effort does that.
Because like the goal is to get into the holes.
Exactly. Yeah,
And
exactly.
that's in like all of these things.
That's the norm. Okay, so those are three ways, okay. Another way you can change stability, so those are examples of changing stability so the atmosphere becomes unstable, right? Warm the ground and destabilizes the atmosphere. Another way you can get an inversion is through what we call a subsidence inversion, which is slowly sinking air in a high pressure, because air that sinks does what? It warms, right? And if you've got very slowly sinking air in a high pressure, it is warming by compression. And at some point, okay, you almost certainly will have an inversion in the upper levels. As that air is sinking and warming, you'll create what is known as a subsidence inversion. And that stabilizes the atmosphere. Remember, an inversion is the most stable form of the atmosphere you can get, okay? Because it acts as a lid. This is one way that you can produce the lid. Okay. So, a quick summary in a simple cartoon. And then we're gonna just leave stability for a bit. You're probably like, thank goodness, move away from this. So, we've talked a lot about getting air to go up, right? The easiest way to cool a parcel of air and bring it to its saturation vapor pressure curve or its dew point is to lift it, right? Rising air cools by expansion. That's a fundamental law. And the reason why we want air to rise is that we want it to reach its lifting condensation level. We want to get it onto the saturation vapor pressure curve. We want to bring it to its dew point, the temperature to which the air parcel must be cooled for saturation to occur. All good? Okay. And then if we get that air to continue to rise, okay, increased vertical motion, what happens? The air continues to cool, but it cools at the saturated adiabatic lapse rate. And as it's sliding down the saturation vapor pressure curve, it's changing phase, right? It's cooling at the saturated rate, which is a lower rate, because latent heat's being released. And your air, your water vapor, you've got water vapor, but you are now condensing and changing phase from water vapor into liquid as that air continues to rise. As it slides down the vapor pressure curve, that moisture is being, I hate this term, but it's being squeezed out as cloud droplets. Does that make sense? So these dominoes all have to come into effect. If you've got an unstable atmosphere and you get the air just to do that, then that's conducive to air rising, reaching its dew point and continuing to rise, okay? But you don't have to have an unstable atmosphere. You can do what we did in 5 a.m. this morning and bring in a cold front and force that air up anyway. Right? But as long as you've got rising air, you will at some point reach the condensation level. So long as you have rising air in that point. All good? We still don't have precipitation. We're not even close to precipitation. So that's the next part of the morning. Right? Is how do we go from getting to the lifting condensation level to forming cloud droplets and then ultimately getting rainfall to fall through those cloud droplets? Okay, so that's where we're headed next. Okay. I know this looks like a bizarre slide, but it is here to illustrate a really important point. Let's just put the first one on here. Here's a tennis ball, right? So I've got three different units here. So these are millimeters. Okay, these are microns. Our friend the micron, remember the electromagnetic spectrum? Okay, we're down here in the infrareds, 10, water vapor, and so on. And then we've got nanometers. I'm not going to ask you to remember these numbers, but I'm putting these up here just to illustrate a point. Okay, that's the size of a tennis ball. That's the size of a period, more or less-ish. Okay, a period is about 800 microns, about 3/4 of a millimeter. Of course, it depends on what pen you're using, but generally speaking, you put a period down, that's where it is. Okay, that's what a cancer cell looks like. That's what a bacterium looks like. Okay, and here is a water molecule. A water molecule down here is in a unit that we call the angstrom. I don't know if you've ever heard of that, right? But it's a tiny, 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 tiny unit. Right? So again, these are 1 micron is 1,000 angstroms. That's 1 micron. That's the size of a clay particle that you cannot see with a naked eye, right? So a water molecule, 2 hydrogens and oxygen, H2O, arranged in this 105 degree, that those axes are about 3.6 angstroms. And that's why you can fit about 1 million of these onto a period. Okay, so I use that just to make the point that when we start thinking about the lifting condensation level and we raise the air a little further, right? That when we start getting condensation occurring, when the water vapor changes phase from water vapor and slows down and rejoins up into liquid water, okay? I know when I first, I started thinking of, okay, it's immediate raindrops. It's not. It's tiny, tiny, tiny water molecules that then have to join together. Okay, so that's why, incidentally, when I said it's a safe assumption at the surface, when you're thinking about a parcel of air, if that parcel of air lifts up, it's going to take all of the water vapor with it, because the water vapor is just so tiny. Any kind of upward movement moves that water vapor up. Oh, I forgot my buddy the virus. Okay. Oh, there's an antibody. I forgot that one too. Never mind. All right, point made. There's water. Way down on the left-hand side. Okay. So how do we go from the lifting condensation level to precipitation? Right? Because if you have a water drop, okay, if you have 2, 3, 4, 5, 10, 100 water molecules jumping onto one another, if that water droplet falls below the cloud base into unsaturated air, it's going to spontaneously evaporate before it ever gets probably a millimeter or 2 below the cloud base. The point here is that once you start getting into a cloud and you start forming cloud droplets, in order to get any meaningful precipitation, you have to grow those cloud droplets. Okay, many times over. So I don't know if this works, maybe a silly diagram, but this is the size of a human hair, 50 to 100 microns, depending on whether you've got thin hair or thick hair, right? So 50 to 100 microns is about a typical hair. Here's a cloud drop. Okay, a cloud droplet is typically about 10 microns. Okay, so if I just go back one for a second, here's a cloud droplet here. Okay, 10,000 nanometers. Okay, we've got thousands and thousands of water molecules that make up a cloud drop. Okay, and 1 million of those make up the period here. Okay, so a cloud droplet is about 10 microns. Fine drizzle fog is about 100 microns, and a small raindrop is about 1,000 microns. And what we experienced this morning were probably raindrops of, I don't know, I didn't look. But they were probably 4,000, 5,000 microns, right? In diameter, 4 to 5 millimeters. So the point here is that you have to start growing, okay, water vapor into liquid water, and you have to start growing it at least 10 times, 10 times, 10 times, 10 times, 10, thousands of times. You have to start growing those cloud droplets into droplets that are big enough so that they can fall through the cloud. Does that make sense to everybody? Okay. So when we get onto the saturation vapor pressure curve, you have nothing except saturated air, right? Now you've got to grow those cloud droplets. On the right is just another cartoon to show that you've got in a cloud or in the atmosphere, you've got what we call updraft, so air moving upwards, okay? And then the size of the raindrop will determine what the vertical velocity is, right? What the downward velocity of the cloud droplet is. That's a function of the cloud size. So let's say you've got an updraft moving vertically upwards at 3 meters per second, and you've got a small raindrop here, a very small raindrop that based on its diameter has a downward fall speed of 1 meters per second. It's still going up at about 2 meters per second, right? At some point in that cloud, the vertical uplift will balance the terminal velocity of that size of the raindrops, and it'll remain suspended. And then at some point, you will grow that raindrop to a size where it has a downward velocity greater than the updraft. So if your updraft is 3 meters per second, and you've got a really big raindrop that will fall through at 5 meters per second, then it's actually falling down with a relative ground speed of 2 meters per second. Does that make sense? So the point here in this cartoon is that you not only have to grow the cloud droplet big enough to avoid it evaporating, you've got to grow it big enough so it stays suspended in the cloud and grows so that eventually it will fall through. And by the time it exits the base of the cloud here, yes, it'll start shedding water, it'll start evaporating and shrinking because it's going into unsaturated air. But hopefully it's falling at such a speed and it's big enough that it bonks you on the head by the time it reaches. So,
What determines the updraft velocity?
so good question. The updraft velocity is determined by the heating rate and whatever the trigger mechanism is, right? So at 5 a.m. there wasn't vicious ground heating. The upward velocities were so significant in that storm. Why? Because that cold front was coming in and forcing that air vertically upwards so quickly over short distance. It's a great question.
And does that updraft, determine what the ground relative fall speed is gonna be?
The updraft relative to the size of the cloud drop. It then grows big enough for a raindrop.
And it does just switch from going up to down just because of the effects of gravity.
Exactly. The relative full speed. Okay, now here's going to be the most bizarre concept of this morning. You probably thought we've already done that. No, here's it is. So let's start on the left-hand side here. Again, these are very simple. So this is temperature on the bottom. I haven't even put any numbers on here. And here's elevation. Okay. So when you send a weather balloon up, say we sent a weather balloon up right now from the surface, okay, and as long as the ground temperature was above 0 degrees Celsius, so let's say the surface temperature here, I don't know what it is right now, whatever. Let's say the surface temperature here is 20 degrees Celsius, okay, and this shows the environmental lapse rate going up with height. As you go up with height, you're going to get to a couple of critical temperatures. You'll get to the 0 degrees Celsius, which of course is the freezing point, right? So here's the freezing point. And then you're going to get to another level, which is minus 40 degrees Celsius. That's a really important thermal boundary in the atmosphere, minus 40 degrees Celsius. Okay. Why? Because when your temperature is above freezing, then all the water is liquid water. Well, that makes sense. Right, so above freezing, all of your water vapor and your liquid water and your cloud droplets are liquid water. Okay. Above 40 degrees Celsius, so if you're here and you're colder than minus 40, so minus 45, minus 50, kind of where airplanes fly, then all of your water is frozen, it's ice. You've got ice crystals. In other words, water will spontaneously freeze. Temperature is colder than minus 40. Doesn't matter how big or how small the cloud droplet is, how many water vapor molecules you have, got ice crystals. Okay. So those are the easy ones. The middle sector is where it gets funky. Okay. In the middle sector between 0 degrees Celsius and minus 40, you have a combination of ice crystals and water. And you're probably thinking, wait, how can you have water below freezing? that water in the atmosphere is called supercooled water. Okay, it's water that remains liquid water below 0 degrees Celsius, up until -40. And it occurs, and it's because the water molecules are so small in diameter, right? Tiny, tiny, tiny water molecules. Water droplets, very, very fine mist and water droplets. And they're so small that ice crystals cannot grow quickly enough for it to actually freeze until you get to -40. So this is the most important sector of most clouds and certainly most storms. Because just look at the temperature range here, right? If we've got a summer afternoon, let's say it's 30 degrees Celsius, so what's that, 90? And it's going to cool at 1 degree Celsius per 100 meters. So it'll get to 20 degrees at 1 kilometer up, right? It'll get to 10 degrees at 2 kilometers up. At 3 kilometers, at worst, you're at the freezing point, okay? And a lot of thunderstorms go up through to 7, 8, 9 kilometers, maybe 10 kilometers up in the atmosphere. So once you start getting into the guts of any storm, you're absolutely in this region here. By the time you get to -40, you're probably up at, I don't know, 25, 30,000 feet. Okay, so most storms and most clouds with any vertical depth in the atmosphere are a combination of ice crystals and supercooled water, water that is still liquid, but below freezing. That has a very important implication in this discussion. I know that's a really bizarre concept, but that it is what it is. That's what happens in the atmosphere. Okay. So then, finally, let's talk about how we get precipitation. And I'm going to be honest here, folks, we're going to keep it super simple. I'm not going to get into an entire lecture on how we generate the physics behind rainfall. I think that's beyond the scope of what we want to try and do in this course. I'm just going to keep it descriptive and qualitative. Okay. There are two processes that grow cloud droplets into rainbows. Right. The first one is the more complicated one, and we're not even going to tackle the physics behind it. But here's descriptively how it works. Okay. Remember when we put up the saturation vapor pressure curve? And I said when we're here, there's a second curve here, which is ice, and I said, just ignore it. Well, unfortunately, we can't ignore it anymore. Okay, so here we are. We're going to start off simply. We've got the closed container, we've got liquid water here, and we've got a block of ice on the left. Okay, if we let the atmospheres above the block of ice here and the atmosphere above the water, if we just left them alone and we said, okay, come into balance with the atmosphere. Remember, we've got evaporation occurring and condensation, and your evaporation rate is high initially, and then eventually your evaporation rate meets your condensation rate, right? And your vapor pressure is saturated. So this is the saturated vapor pressure over water. Over ice, there is less vapor pressure over ice, because the vapor gradient is more gentle. Okay, much harder to get water to evaporate off an ice surface into the atmosphere than it is off a liquid water surface. I think maybe intuitively that makes sense, but that's what happens in reality. Okay, so over an ice surface, in and around ice crystals, there is less water vapor in an atmosphere around ice crystals than there is around liquid water. Okay. And so what happens if you remove that barrier, right? If you remove that barrier, then you get the water molecules start mixing across that barrier, okay? So remember, fluid moves from a high gradient, a high potential energy gradient to a low. Air moves from high pressure to low pressure, right? So here we've got a high vapor pressure to a low vapor pressure, so water molecules start moving from right to left. So the vapor pressure over the water goes down, and the vapor pressure over the ice surface goes up. In the atmosphere, that is essentially what happens when you have supercooled water and ice crystals. Okay? Supercooled water and ice crystals. So meteorologists often talk about the Robin Hood effect. So the process is known as the ice crystal process. And the ice crystal process It's also known as the Bergeron process after the Swedish dude who experimentally showed this to work in the lab. This is basically what happens in the cold sector of a cloud, in other words, between 0 degrees and -50. Okay. When you've got ice crystals and water droplets, because of the vapor gradient that occurs between the water droplets and the ice crystals, the water droplets start shrinking. It starts evaporating, and those water molecules jump across and cause the ice crystal to start growing. Okay. That's essentially the ice crystal process, where water vapor is robbed from the water droplet and starts growing the ice crystal simply because of the vapor gradient between the two over very, very, very small distances within a cloud. Does that sort of make sense? If it doesn't, don't panic about it. I'm not going to ask you it in the exam, right? But I just want you to know that in that sector between freezing and -40, this is the way in which ice crystals grow. They grow because of the vapor gradients around water relative to ice. So those ice crystals are continuously growing as the water droplets are evaporating. That water vapor is being robbed. So the reality is that most rainfall starts off as snow, as ice crystals, that then have to fall through the atmosphere and eventually melt. Okay. So that's the ice crystal process, or the Bergeron process, where ice crystals grow at the expense of water droplets. And the other process only occurs in the warm sector of the cloud. So the other process occurs above freezing point. And that is the process that we refer to as collision and coalescence. And that is just simply water droplets bumping into one another and merging. Kind of like if you're driving, I saw this happening on my windscreen this morning driving, right? If you've got rain droplets moving down your windscreen and it suddenly scooches down the windscreen and then it merges with another one, bloop, and it gets bigger, and what happens to that bigger one? And it comes down a little faster, and if it sucks another one and it gets bigger and bigger, that's exactly what happens in warm clouds, where the temperature is above freezing. Okay, so it's raindrops that are growing by capturing other cloud droplets, sucking them in.
Does the Bergeron process change the temperature of the cloud?
No, good question. No, I don't think so. I'm gonna
Is it
say,
like the transfer of heat?
That's a good question. I've never seen that come up. Does it change the temperature of the cloud? I don't know. It's a cloud droplet.
Like I assume it has to become colder and it's gonna form ice.
Yeah, you would imagine it would. Let's just think about that, because you're changing phase from liquid water back into ice, right? So that latent heat is being taken out of the environment. That's what I've never really thought about. Marty Pants question. I'm gonna have to go, hey, sorry. What happens? I've never seen anybody talk about it. You know, does that change the stability? I don't know. So, you gotta think about that. Someone gotta think about it. You would think it would, but I don't know if that changes the dynamics.
Well, like if it's already in that colder temperature range.
Yeah,
But would it fluctuate in between that?
you would imagine it would, but not enough to do anything significant, right? Over that kind of scale. I don't know. You have to look at that. Good question. Interesting question. So those two processes, whether or not they change the internal dynamics, are the two processes that cause ultimately raindrops to get big enough. You've got to get ice crystal growing large enough, and then through collision and coalescence. Eventually, raindrops can only reach a certain diameter. We don't get raindrops falling the size of basketballs, thankfully, right? Because friction just shears them apart and they break up. So, you know, 4 to 5 millimeters is about it. So the type of precipitation that we actually see at the ground, okay, and we still haven't even got to clouds, so I'm going to probably just end a little early because I've got a lot of information. So the type of precipitation that we get at the ground then just simply depends upon the temperature profile. Okay, so 4 temperature profiles that are simple here. This is the 0 degree line, and if this is what your environmental lapse rate looks like, okay, and we've just drawn it here with an inversion there and decreasing. That's of no real significance in this example. The entire temperature profile is below freezing, meaning that what you'll get at the ground is snow.
If, this is kind of going back, but if the rain droplets can only hit a certain diameter, then how do we get like all size hail?
Oh, that's a different thing. Yeah, good question. I haven't touched hail. I'm gonna come back and talk about hail when we look at thunderstorms. Yeah. Because a raindrop of 4 diameters just doesn't suddenly go, "Hey, shoot, I'm a piece of hail," right? What you've got to actually do, if you think about the vertical velocity cartoon with the updrops and the downdrops and the terminal velocity, you've got to have that growing and suspended. And Nick, I think you may have intimated this, you've got to have that, circulating within a cloud for a long period of time to actually start rhyming or starting to get bigger and bigger within the cloud. So if your temperature profile is below freezing, then you'll get snow, right? If your temperature profile looks like this, if it's above freezing for any significant depth, as long as your frozen precipitation can melt, then you'll get rain. So even heavy rainfall in the tropics starts off as ice crystals very high up. And then the other two that I think are sort of interesting here are when do we get sleet and when do we get freezing rain, right? So in the sleet here, you've got a deep freezing layer, okay, and a warm layer aloft here. Got to have warm air where your ice crystals melt into rain, okay, and then they can refreeze over a deep enough layer to cause sleet, as opposed to a very shallow freezing layer, where your raindrops will freeze on contact. So they'll essentially get super cool and then freeze on contact with a shallow freezing layer. So the vertical temperature profile of the atmosphere is what determines the type of precipitation you get around. Makes sense. So that's the end point of why we started off with the importance of the saturation vapor pressure curve, bringing in air parcel to saturation, the overall stability characteristics of the atmosphere. Will that air go up or down? And then how do we actually then grow cloud droplets to become meaningful raindrops? Remember, as they go through the base of the cloud, they're going to start evaporating anyway. Right? If you've got 1 million water molecules on a period, and then you've got a raindrop that's 4 or 5 millimeters, you've got tens of millions of water molecules. You can afford to shed a few before it actually hits the surface of the ground. Okay. I'm going to stop there. So on Thursday will be cloud classification. Cloud classification is real simple, and we'll probably just spend 20 minutes on it, something like that. And then we'll start the thermodynamics. Things on Thursday, I can't remember if I put this in the email, but bring a couple of things that give you some different colors. I want you to bring like an entire Crayola set. But it would be helpful if you had a pencil, a pen, and maybe a green and a red or something, right? I'll provide all the plotting. What we'll do with the thermodiagram, the only way to really do it is to work you through an exercise. And so just a heads up, when we get to the thermodiagram, ultimately you'll take home exercise. I'm going to work through what you're taking at home. It's the best way to do it. You plot this, plot that, and so you can actually get it through a fully worked exercise before I send you off to the wild west. All right. Awesome. Good. Yep, good one. Yeah. Okay, we're gonna put your question. No.
Yeah.
Is it growing?
Or is it kind of the same?
It's. It's a big.
Mom heard the tornado sirens at 5 AM and round up the whole family, made us all sit.
There you go. See, now at the end of the stories, you'll be able to okay, kill everybody. We're good. Or
I'm so tired. I'm gonna get my
I know.
revenge somehow.
our new puppy.
Yep.
the list.
Yeah, our dog is not happy today. Oh, thanks.
Yeah.
I know, sorry.
Have a good one.
But municipal. Everything else.